Good afternoon. We had made a passing mention about braking in an induction motor, especially when we were talking about V by F control. So we said that at lower frequencies, normally we are going to compensate for stator drop so that the torque is not reduced tremendously. So the stator drop needs to be compensated for. Um, but when we are compensating for the stator drop, what we do is E plus whatever is I1 multiplied by R1 plus JX1, we add this stator drop. This is what is the stator drop. And we just take this as V1. So we are going to keep this as V1. So if I have a 400 volts, 50 hertz induction motor, if I am operating this at 5 hertz, I assume that if V by F ratio is a constant, I have to apply 40 volts. But rather than applying 40 volts, if I try to add this stator drop, let us say stator drop is 30 volts or something like that. So instead of applying 40 volts at 5 hertz operation, I might end up applying 40 plus 30, which is 70 volts for obtaining a good amount of torque even at 5 hertz. That's what we said. So if we compensate for the stator drop, we'll be able to get a good amount of torque because the air gap EMF, what is available, will not be decreased tremendously even at lower frequencies of operation despite the stator drop. But if use a similar situation for regenerative braking, that's what we mentioned in the last class. So in regenerative braking, if I try to apply the same kind of stator drop compensation, what is going to happen under that condition is E minus I1 multiplied by R1 plus JX1 will be V1. So if I am making this as 70 volts, when regenerative braking at 5 hertz is being implemented, then E will be equal to the 70 volts plus stator drop. So if the stator drop happens to be, say, 30 volts, this is going to be 70 volts plus 30 volts, which will actually make E equal to 100 volts, which is way, way too high. So 100 divided by 5, this is going to be E divided by F, which is proportional to flux. Normally, what I should be seeing is 40 divided by 5. Instead of that, I'm looking at 100 divided by 5, which means the flux will be increased tremendously and saturation is bound to occur. So that's not a good situation. That's what we said for regenerative braking. If I apply the same kind of correction which is corresponding to the stator drop. When I'm doing motoring operation, it is fine. But when I'm actually into regenerative braking operation, it can result in saturation. That's what we said. So in this context, let us try to look at the braking of induction motor, exactly how the braking operation is implemented in induction motor. Again, in induction motor, there are 3 types of braking. The first and foremost braking which we are going to talk about is regenerative braking. The second method of braking that we will be talking about is plugging. So regenerative braking we already touched upon during V by F control, but we will again, and even we looked at this when we were talking about slip energy recovery, especially when we are injecting a voltage from the rotor side. So we will revisit this now. And the second type of braking that we encounter normally is plugging. The third type of braking that is implemented is called dynamic braking. One major difference between dynamic braking in a DC motor vis-a-vis dynamic braking in an induction motor. In an induction motor, it is a singly fed machine. So if this is my induction motor stator and this is rotor, this is connected to the three-phase supply. So this is going to be connected to the three-phase supply. And when we are talking about dynamic braking, we are supposed to remove the connection to the supply, and we are supposed to take out the three terminals of the rotor. We should be able to connect it to, or the armature, we should be able to connect it to the resistance. That's what we talked about earlier. But in this particular case, if it is a cage induction motor, the rotor is not even accessible. So that is the first and foremost thing. So in dynamic braking, we should be able to access the power supply either from the rotor or stator. The stator was originally connected to the three-phase supply. I am going to disconnect that from the three-phase supply. So I am disconnecting that from the three-phase supply. Now the rotor side is not accessible. So can I connect three-phase resistance here? So from the stator side, can we connect three-phase resistance? But if we have to connect three-phase resistance, that means the machine should be able to work as a generator. And for the machine to work as a generator, I should have air gap flux. But if I don't even connect this to the three-phase supply, the air gap flux will collapse. So we will not have any air gap flux. This will be absent. So even for implementing dynamic braking in the three-phase induction motor case, we need a source of excitation. So if we don't have a source of excitation or flux, then it is not going to work. So in that sense, we will be able to have a source of excitation or a reactive power source either by connecting capacitors in the three-phase line. So that is generally known as capacitor braking, or we may be able to connect a single phase AC source maybe just in two lines of this particular induction machine. So in that case, we call that as AC dynamic braking. So we may call that as AC dynamic braking if we are connecting a single phase AC source on the stator side. Rather than that, if we connect a DC source on the stator side, we call that as DC dynamic braking. And if we are going to connect all the three phases of the induction motor, either in series or in parallel, only if the terminals are accessible, both terminals of the stator winding are accessible, we will be able to connect them in series or parallel. In that case, we are going to have, for example, if I'm going to have a three-phase winding, stator winding like this, and I want to connect all three of them in parallel. So that means I'll have to connect these three terminals together, and I have to connect the source in between these two. So I should be able to connect the source here. So I can connect a DC source or AC source like this. Now it is as good as connecting all the three phases in parallel and connecting a DC source. So all of them will carry current which are in phase with each other. So we are going to see that all the three-phase currents are going to be in phase with each other. So that is the reason why we call this as zero sequence braking. Because if you are familiar with symmetrical components, we generally say zero sequence component is actually cophasal. All three of them are going to be cophasal, A phase, B phase, and C phase. And that's the reason we call that as zero sequence braking. So we'll look at each one of them in detail in the subsequent sections now. So let me start with regenerative braking. So in regenerative braking, basically you are going to make the machine work as a generator. So we are going to have generator operation for the machine. So the generator operation of the machine takes place only if two conditions are satisfied. One is the synchronous speed has to be less than the mechanical speed of the machine or the rotor. The second one is there should be at least a source of reactive power or source of magnetization. To magnetize the machine, there should be some kind of source available. Only if these two conditions are satisfied, generator operation will take place. So under this condition, what happens is, because synchronous speed is less than the mechanical speed, if I calculate the slip, which is corresponding to omega s minus omega m divided by omega s, this will be negative. So the first and foremost thing is the slip is going to be negative during regenerative braking operation. So if the slip is negative, let us try to take a look at qualitatively what happens in the machine. So this is the stator and here is the rotor. So the rotor conductors are actually located in the periphery of the rotor cylinder. So this is where the rotor conductors are located. Now, we are going to have a revolving magnetic field which is rotating at omega s. And we are going to have the rotor rotating at a speed which is higher than this omega s. So omega m is going to be higher than omega s. So if somebody is sitting on the rotor and trying to look at what is the speed of the revolving magnetic field, it is going to look as though it is rotating in the opposite direction like this. And that is going to be omega s minus omega m, rather omega m minus omega s. I'm just writing this as the magnitude. The difference between omega m and omega s is going to be the speed visualized by the rotor conductors when they look at the stator's revolving magnetic field. And it is going to look as though it is in the opposite direction. So if I am looking at what is the kind of EMF induced in the rotor conductors, if in motoring operation, if the induced EMF had induced EMF in the rotor had ABC phase sequence. Now, in generating operation, because the relative velocity is in the opposite direction, it is going to have ACB as the phase sequence. So the induced EMF in the rotor will have reverse phase sequence as far as the kind of induced EMF is concerned. So if we actually look at it, if we say that the input power to the induction motor normally is going to be whatever is the stator voltage, stator current, cos of angle between stator voltage, the stator current, 3 times that. This is the input power to the induction motor. So if I draw the phasor diagram normally, I am going to have the voltage like this. And generally, I am going to have the current in such a manner that I'm going to have the current somewhat like this. So this is going to be IS. Now, I can say that this is the magnetizing component of current or which is responsible for flux producing. And this one is corresponding to the torque producing component of current. So this is going to be something similar to I2 dash. Because the rotor side current is the one which is producing the torque. So I can call the torque producing component of current is very similar to the rotor side current. So it is I2 dash. But this is the case when I'm talking about motoring operation. So this was our phi s. If I try to look at it, what is the phase angle between voltage and the current? That will be phi s during this particular situation. But when I am talking about generator operation, the torque that is being produced is a negative torque. After all, it is generating electricity. So obviously, the torque that is being produced or developed by the motor is going to oppose, by the machine is going to oppose whatever is the applied torque. So which means the actual torque producing component of current is going to be reversed as far as its direction is concerned. So this is going to be I2 dash under generating condition, whereas this is going to be I2 dash under motoring condition. But the magnetizing current will not change. The magnetizing current still has to come from the supply. So that is not going to change. So when I add these two, I am essentially going to have a current which will be along this direction. So this is going to be actually IS during generating condition, whereas this is going to be IS during motoring condition, which means the phi s value, what happens during the generating condition. So this is going to be the generating condition, whereas this is going to be the motoring condition. So the power factor angle phi s becomes greater than 90 degrees in generating condition. So if I look at the operation basically in terms of power, so power which is actually 3 times Vs Is cos phi s, and phi s being greater than 90, I'm going to have negative input power. So if I'm going to have negative input power, that means the machine will deliver power, deliver real power to the three-phase mains. So you are going to see that the real power is delivered by the machine to the three-phase mains. So it is going to work as a generator. And just to look at again from the point of view of the equivalent circuit, if I say this is R1, this is X1, this is Xm, and I'm going to have R2 dash divided by S, and I'm going to have X2 dash, and this is what is the overall equivalent circuit of the induction machine. I'm still connecting this to the mains. So there will be some voltage, definitely V1, that is being applied from here. There is no doubt. That is what is really causing the flux to be produced in the air gap. So now because this S is negative, slip is negative. So we are going to see basically that we are having, first of all, reverse phase sequence of voltage induced here, and the current, rather than the torque becoming positive like motoring operation, in this particular case, the torque will be negative because the slip is negative. You can see that 3I2 square R2 dash divided by S. This is going to be the power input to the rotor. And that itself is going to be negative because we are going to have the slip value to be negative. So now the rotor is going to supply the power towards this side. So you are going to see that basically the power is supplied to the mains like this. This is what is going to happen. So in generator operation, the major difference comes because of the synchronous speed being less than the mechanical speed, which causes the phase sequence of the rotor induced EMF to be reversed. And even the current direction is going to be reversed because of the fact that we are having the slip to be negative. So rather than the rotor absorbing or taking in power, it is going to supply back the power, and the mechanical energy stored in the rotating parts of the machine that is going to be converted into electrical energy with the help of the air gap flux, which is already established and which is not collapsing. That is not collapsing only because it is connected to the power supply continuously. And the generated electricity will be fed back to the mains. So this is the way the regenerative braking works. So the regenerative braking, as far as the expressions are concerned, everything is pretty similar. Only thing is we normally write E plus I1 multiplied by R1 plus JX1 equal to V1. And this is during motoring. Whereas during generator operation, E minus I1 multiplied by R1 plus JX1, that will be the terminal voltage V1. So this will be during generating operation. And another thing is, if we say that 3I2 square R2 dash divided by S omega S, this is essentially the torque. The expression is valid in both the cases. Only difference is S is positive during motoring, whereas S is negative during generating operation. And if I write the expression in terms of voltage 3V1 square R2 dash divided by S omega S, again S is going to be negative value, and we are going to have R1 plus R2 dash divided by S the whole square plus X1 plus X2 dash the whole square. So this is going to be the expression corresponding to torque even in generating operation. Only thing you have to remember is this R2 dash by S itself becomes a negative value because slip becomes a negative value. So what you see as the overall impedance, the resistance component of the impedance will decline quite a bit. So due to which you might see that there is a slight increase in the torque production during generating operation. Now, if I try to draw the characteristics corresponding to generating operation, let us say this is the speed torque plane, and this is going to be the torque, and this is going to be the speed. So under normal condition, I'm going to have a characteristic somewhat like this. This is going to be the characteristics as far as the induction machine is concerned. Now, this is the synchronous speed. So we know that this is corresponding to synchronous speed. Now we are talking about the operation above synchronous speed. So very clearly this characteristics has to be extended somewhat like this. So this is the motoring zone, whereas this is going to be the generating operation. So here TE is positive, whereas here TE is going to be negative. And the speed is higher than the synchronous speed. So if I try to calculate the total regenerated power at this point, for example, although the torque value still remains at TE max, if I may call this as TE max, this will be minus TE max, and this will be plus TE max. So if I try to calculate what is the power at this point, this will be, if I may call this as omega M1. So this will be omega M1 multiplied by TE max. Whereas under this condition, I'm going to have this point, if I try to calculate the power, if I say that this is omega M2, which is much higher than omega M1, I'm going to have omega M2 multiplied by TE max. So the regenerated power could be much higher than whatever is the motoring power which you look at when you are having subsynchronous operation. So in supersynchronous operation, just because the speed is higher than whatever is the synchronous speed, you can see that the regenerated power becomes quite high. But even when we are doing regeneration, generally we ensure that we don't operate beyond this TE max point. We operate it only from omega S to 1 plus S max T multiplied by omega S. We don't try to operate it beyond that. And in motoring, this is during regeneration. And during motoring, we will operate from omega s until 1 minus s max t times omega s. We would not like to go beyond that. So this is the point which is corresponding to s max t. This is the slip at maximum point. So normally we operate it only between, if I am talking about regeneration plus motoring, we would not operate beyond the speed. We would not operate generally below the speed in the induction machine so that it always remains in stable operating condition. The regenerative braking obviously would not be working if we try to go below synchronous speed, because below synchronous speed, the torque automatically becomes positive. So you cannot call it regenerative braking anymore. So with the constant frequency supply, if I'm talking about a constant frequency supply, we cannot have regenerative braking cannot take place, or regenerative braking cannot work, does not work below synchronous speed. So if speed is less than synchronous speed, it's not going to work very well. Okay. But if I'm having a variable frequency supply, so regenerative braking with an inverter. If I'm going to have an inverter, in that case, you can say, if let us say this is the operation, the speed tag characteristics of an inverter fed induction motor. This is omega m and this is TE. So let us say I'm going to have a characteristic somewhat like this. So this is where the motor is working. Let us say the operating point is somewhere here. Okay. Now we want to implement regenerative braking and gradually stop the machine. So if I want to do that, I should look for various characteristics which are corresponding to lower and lower frequencies. So I'm going to have various characteristics somewhat like this. So this is the operating point A, and let us say this is 50 Hertz. And let us say this is corresponding to 45 Hertz or 42 Hertz or something like that. So if I abruptly change the frequency to 42 Hertz, and if I try to look at the speed, because the speed cannot change immediately, the speed remaining the same, it is going to migrate from point A to point B. So this is point B. So when it is operating at point B, it is already in regenerative braking mode, because the speed happens to be, if I may call this speed corresponding to omega R1 or something like that, this particular speed at A as well as B, that happens to be greater than the synchronous speed at 42 Hertz, we are going to have the machine traversing this path. Now, once it reaches this particular operating point, which is corresponding to C, let us say I'm going to again change the frequency of the inverter in such a way that it is brought to something like 30 Hertz. So when it is brought to 30 Hertz, I can again see from point C, if the speed still remains the same, it will slowly migrate to point D. And point D is again in the regenerative braking zone. So because of which, again, it is going to go along this path. And let's say it reaches point D. So once it reaches point D, I can again reduce the frequency probably to 20 Hertz or 18 Hertz or something. So theoretically, I should be able to implement regenerative braking almost until zero speed. That is essentially because I have the frequency of the inverter under my control. So by adjusting the frequency of the inverter in such a way that omega s of the inverter frequency, which is actually the revolving magnetic field speed, I can adjust that inverter frequency in such a way that it is smaller than omega R1 or omega R2 or omega R3 and so on. If I may call this as omega R1, I should call this as omega R2 and I should call this as omega R3 and so on. So I should be able to adjust the inverter frequency in such a manner that the revolving magnetic field speed is smaller than the actual rotational speed of the rotor, so regenerative braking can be implemented. So in general, regenerative braking can be implemented very, very well using an inverter whose frequency can be controlled as per our requirement. So that is the reason why in many of the electric vehicles, we tend to implement regenerative braking so that a huge amount of energy can be saved and unnecessary heating of the rotor and stator parts can be completely avoided. Okay. So now let us go over to the second method of breaking off induction motor, which is known as plugging or reverse phase sequence breaking. In the case of DC machine, we call that as reverse current breaking. But here we are going to change the phase sequence of the machine itself or the stator supply itself. That's why we call this as reverse phase sequence breaking. So during normal working condition, if let us say these are the three phases of the induction motor, let me call this as A, this is B, and this is C. And this is going to be my rotor. Maybe it is a squirrel cage rotor. I'm showing it like this. Now, this is connected to A phase of the supply. This is connected to the B phase of the supply. And this is connected to C phase of the supply. So this is exactly ABC phases are connected to ABC phase of three-phase supply. Now, when the motor is running, if I want to implement plugging, what I should do is the same three-phase winding. Let us say this is A, this is B, and this is C. Now, what I'm going to do is I'm having the three wires brought out for the machine. And let's say these are the three-phase supply. Maybe this is A, and this is B, and this is C. What I'm going to do is I'm going to connect the B phase supply to C and C phase supply to B and A phase will be connected to A. Whereas, of course, my rotor is right here, which is already rotating. So this is going to rotate continuously. But the moment I change the phase sequence of this particular induction motor stator supply, let's see what happens. So what I would have been seeing in motoring operation. So this is motoring operation, whereas this is plugging operation. So in motoring operation, what I would see is, if let us say this is my stator, cylinder, and I'm going to have omega S, which is rotating in this direction. And here is my rotor, and it has conductors in its outer periphery. And we are going to have the rotor rotating in the same direction as that of revolving magnetic field. So this is rotating at omega r. So I'm going to have omega s minus omega r divided by omega s as the slip in the motoring operation, right? Whereas in plugging, let us see what happens. So I am having this as my stator cylinder, and this is the rotor cylinder, which is having conductors at its outer periphery like this. And we are going to have here omega s now in the opposite direction, because instead of ABC phase sequence, I'm having ACB phase sequence. So obviously the revolving magnetic field is going to be set up in the opposite direction. But if I try to look at the rotor abruptly cannot change its direction of rotation. So that is going to be omega r. So if I try to calculate the slip under this condition, now the speed of the revolving magnetic field has to be specified by minus omega s, and the speed of the rotor is omega r, so that has to be subtracted from minus omega s, and this is divided by minus omega s. So if I say this is s, this is essentially s. So in that case, I should be able to write this as minus omega s, and omega r can be written as 1 minus s times omega s and divided by minus omega s. Okay? Because omega r is 1 minus s times omega s, if I'm trying to look at the original expression for the rotor speed. So this can be written as 1, and I have to write this as plus, and I have to write 1 minus s. So this is going to be 2 minus s. So the slip now comes out to be 2 minus s. If I say that the normal slip of the induction motor is less than 4% or 5%, so I'm going to have here the 2 minus s coming out to be 1.96 or 1.95, or it is very, very close to 2. So during plugging operation, the first and foremost thing we see is the slip is going to be very, very high, and it is going to be really close to 2. That is the first thing. So in which case, if I try to again draw the equivalent circuit of the induction motor, this is R1, this is X1, and I'm going to have XM. I'm deliberately neglecting RC. Now I'm going to have R2 dash divided by 2 minus S as my rotor resistance side. And this is going to be X2 dash. Now this entire thing is now forming the part of the total equivalent circuit of the induction motor, and this is going to be V1. Of course, this V1 is, if I try to look at it, it's a per phase voltage, but it is going to be with reverse phase sequence. So in the motoring region, when I was talking about motoring operation, we were having the rotor impedance to be R2 dash divided by S plus JX2 dash. So if S is 0.01 or 0.02, the original value of R2 dash will be multiplied by a factor of 100 or 50. So this is going to be pretty high. The rotor impedance will be high during motoring operation. Whereas when I talk about plugging operation, I'm going to have the rotor impedance Z2 to be equal to R2 dash divided by 2 minus S plus JX2 dash. And one more thing we have to realize is, because the slip has increased to 2 minus S, the frequency of the induced EMF, which is causing the rotor current to flow, that will also increase tremendously. The frequency will be definitely increasing, due to which actually the reactance which is visualized in the rotor circuit, that will also be increased normally. But of course, we have normalized everything by dividing by the 2 minus S factor or the slip factor. Now, R2 dash divided by 2 is actually going to decrease the resistance value. So we are going to have low resistance value as far as the rotor equivalent circuit is concerned. So we are also going to have low impedance as far as the rotor side impedance is concerned, due to which we are definitely going to have a very, very large current. The I2 what is flowing here, or I2 dash what is flowing here, will be pretty large. But if you look at the resistance component, because the resistance is small, the actual power that is imparted to the rotor circuit, or the rotor input power, is not so high, although the rotor current is very large. So the plugging operation is not really going to produce a large amount of torque. The plugging torque is going to be pretty small as far as the induction motor is concerned. So let me try to again draw the speed torque characteristics corresponding to this particular plugging operation. So let me again draw this. So this is the x-axis, and this is going to be the y-axis, and this is omega m, and this is going to be TE. And let us say this is the normal characteristics of the induction motor. We said that this is S equal to 0. This is S equal to 1. So this definitely has to be S greater than 1. But this is corresponding to ABC phase sequence supply. So this will correspond to ABC phase sequence supply. Whereas if I am trying to look for ACB phase sequence supply, the synchronous speed is going to be on the other side. This is corresponding to a synchronous speed of omega s. So if I try to look at a synchronous speed of minus omega s, I have to start my characteristics from here. So I should have a characteristic somewhat like this, and it should go on to the other side like this. So this will be the characteristics as far as ACB phase sequence supply is concerned. So if originally I was operating at a point where this is the operating point of the induction motor, and at this point I'm abruptly going to change the phase sequence of the supply to ACB. So this is actually the operating point A, and I have not really allowed the rotor to come down in speed or something like that. Abruptly I have changed the phase sequence of the supply to ACB. So from A, it is going to go into point B. So when it comes to point B, if I try to look at how much is the torque developed, the braking torque is going to be very, very small. It's not much. But if I try to look at the current, I can draw the current. The current generally at synchronous speed, the current is going to be only the magnetizing current, but it is going to increase further and further. And at S equal to 1, the current will be as high as almost 5 to 8 times the full load current. And the current will keep on increasing further and further. So this is the kind of variation you are going to have as far as the current is concerned. So this is the kind of variation you are going to have in the current. So the same way I can draw for ABC phase sequence supply also. So this is the kind of variation you're going to have as far as the stator current is concerned. So the stator current keeps on increasing with the slip, whereas the torque is definitely not, it doesn't commensurate with the increase in the stator current. So plugging is not really going to give a very good amount of braking torque. And one more thing that needs to be said is, if I continue to allow the motor having ACB phase sequence supply, then it will actually come along these characteristics and it will start rotating in the opposite direction. So from ABC phase sequence supply, when I change over to ACB phase sequence supply, you would see that the current drawn by the induction motor is very large and the torque developed is small and the braking takes place. the speed comes down to 0 and then it starts accelerating in the opposite direction if I don't turn off the power supply at this point. We need to turn off the power supply at this point if we really want to stop the machine. So this particular opening of the power supply needs to be done with something like a speed sensitive switch, which can be actually operated by a centrifugal switch. Centrifugal switch is the one which senses the centrifugal force. So when the speed becomes 0, the centrifugal force will also become 0 and immediately the switch is supposed to open the power supply. So if we really want to have a good amount of torque during plugging operation, then what we need to do is to increase the rotor resistance. If I increase the rotor resistance, I will have characteristics somewhat like this. So if I try to increase the rotor resistance, so let me draw this once again. So let us say this is the normal characteristics of the induction motor. If I increase the rotor resistance, I'm going to have the characteristics drooping further and further. So if I am talking about this as the synchronous speed and original speed torque characteristics was somewhat like this, then from this particular operating point, which was the original operating point of the machine, it would be able to generate a good amount of torque if the rotor resistance can be varied. So here, this is the direction in which R2 increases. So if I increase R2 in such a manner that a good amount of braking torque is generated at the plugging point, in that case, that can be achieved only in the case of wound rotor induction motor because I need to play around with R2. If I don't play around with the rotor resistance, then I may not be able to really, adjust the characteristics in such a way that the plugging torque becomes quite high. That is not going to be possible. Okay. So plugging can be implemented with a wound rotor induction motor advantageously such that a good amount of braking torque is developed. So in plugging, what is done is initially when the machine is working on ABC phase sequence supply, eventually we switch over to ACB phase sequence supply when plugging needs to be implemented. And that actually causes a large current to be drawn and a meager amount of plugging torque to be developed. But if you want to improve that performance, only way is to increase R2 value. So that can be done only with respect to wound rotor induction motor. So plugging is not a very good option for squirrel cage induction motor, to be precise. Now let us try to look at dynamic braking. So if you may recall how we implemented dynamic braking. In the case of DC motor, what we did was simply to disconnect. If you may recall in a DC motor, if this was the DC motor and probably this was like a shunt motor, we were having the supply given from here and this was plus and this was minus. So this was the normal motoring operation. And when we wanted to implement dynamic braking, what we did was we simply disconnected the power supply and connected a resistance. This is what we did. Okay. So still this was plus and this was minus and this was the braking resistance that we incorporated. The current was flowing in this direction, whereas here the current was flowing in this direction. So the armature current, what we saw originally was in this direction, whereas here the armature current happened to be in this direction because the back EMF was plus here and minus here. So the back EMF was acting like a source and it was also passing the current, field current even during braking operation. So this is what was dynamic braking as far as DC motor was concerned, if you may recall. But in the induction motor case, it's pretty much different. We are having, let us say, this as our induction motor. And of course, rotor side is not connected at all. We are just having rotor conductors like this. And the three-phase supply is connected here. So the moment you disconnect three-phase supply, you are going to have the flux collapsing completely. The rotor flux may hold on for a very, very short while, but that will also collapse because there is no source of reactive power at all. So if I want to implement dynamic braking, I have to have a source of reactive power. So based on the source of reactive power, we already classified the dynamic braking. If you may recall, in the beginning of this class, I said that there are 4 types of dynamic braking. One is where capacitor will give the flux source. And the second one is AC power supply, single phase AC supply may be connected. The third one may be a DC supply may be connected at the terminals of the induction motor. And finally, all the windings of the induction motor may be connected in series or parallel. So we call that as zero sequence braking. So let us first start with capacitor braking. So in capacitor braking, what we are going to do is when the induction motor stator is connected to the three-phase supply, simultaneously, we may have three-phase capacitors, maybe star or delta connected capacitor, whatever may be the case. Here I'm showing a star connected capacitor that is also connected here. So let us say these are C1, all these values are C1. Per phase value is C1. Okay. And if I say that the voltage per phase is something like V1, so I can say V1 square omega C, where omega is the power supply frequency, that is going to be the reactive power supplied by the capacitor. So the reactive power supplied by the capacitor will be V1 square omega C1, where V1 is the per phase voltage of this three-phase supply. Okay. So if I open this supply, let us say I have the three-phase supply here, I'm going to open these switches and close the capacitor switches, or I could have closed the capacitor even earlier, depending upon if I want to have a power factor improvement, the capacitor could have provided the required power factor improvement for the induction motor itself. So the entire system consisting of induction motor, three-phase supply, and the capacitor would be working at leading power factor or unity power factor, as the case may be. So we would see that generally the capacitor will be helpful when you are connecting an induction motor to the three-phase supply to improve the power factor, but this can also come in handy in terms of braking. So the power supply, the three-phase power supply switch is opened and capacitor switch, if I may call this as SW2, and if I may call this as SW1. So SWN1 is opened and SW2 is closed. So when it is closed, now what is going to happen is, look at the induction motor equivalent circuit again. This is going to be R1. This is going to be X1. And I'm going to have this as C1 now. And I have the magnetizing reactance here. So if I neglect R1 and X1, I'm going to have this like a resonant circuit. C1 and Xm, they are going to exchange energy between themselves. So what I will have is a magnetization characteristics for Xm, which is somewhat like this. So it is going to start from residual magnetism and then it is going to go like this. So this is going to be the variation. So this is corresponding to Xm. So I'm going to have E versus Im. How? That is really depicting itself. This is given by the red color curve. On the other hand, if I try to look at what is the kind of characteristics the capacitor will display, I should say whatever is flowing through this circuit, if I may call this as some I. So I multiplied by XC, that is going to be whatever is the voltage that is manifested by this XM also. So I can say that that is E. So if I may call this as I multiplied by XC, that should be approximately equal to E. So I should be able to draw that as a straight line because capacitor line will be something like this. So this is going to be I multiplied by XC. So that is I divided by omega C. So this is going to be the kind of characteristics I'm going to see. Now the intersection of these two, wherever it happens, that is going to be the operating point of the generator at a particular speed, where omega is the speed at which the rotor is running. The rotor is running at omega, because of which there will be an induced EMF which will be manifested in Xm, which will also be corresponding to the frequency omega. Now, whatever is the energy that is generated, and that will be dissipated to that power will be dissipated to some extent in R1. There will be somewhat some resistance associated with Xm as well as C1. So there is going to be definitely reduction in the energy that is there in the rotating parts. So what is going to happen is omega will come down. So omega, this is corresponding to, let us say omega 1C, and this is also corresponding to omega 1. Now, when the speed comes down, so from omega 1, it is going to come down to omega 2. So this is omega 2 is less than omega 1. When omega is reduced, I'm going to have the next characteristics, which is actually going to go up slightly. So this will be corresponding to omega 2. Whereas the magnetization characteristics, which is actually proportional to the frequency or omega, that is actually going to come down because of omega coming down. So this is going to be the next characteristics, which is corresponding to omega 2. So this has been corresponding to omega 1, whereas this is corresponding to omega 2. So due to which I'm going to have the point of intersection somewhere here. This is going to be the operating point. So this is corresponding to the operating point at omega 2. So like this, I am going to have, as the speed comes down further and further, I'm going to see that the next point may not even have any intersection. I may have this as omega 3, whereas I may have my magnetization characteristics going beneath this. So this may be at omega 3. So I may not have any intersection point at all between the magnetization characteristics and capacitor load line below a particular speed. So the capacitor braking can work quite well for the induction motor, but only until particular speed. So the capacitor braking works well for an induction motor, even for cage induction motor. But below a particular speed, it cannot work. That is because the reactive power provided by the capacitor may not be sufficient even to excite the entire machine so that it generates some tangible voltage. So we are not going to be able to implement capacitor braking below a particular speed. I would like you guys to draw the characteristics, speed torque characteristics for capacitor braking, specifically for two different values of capacitor. So we'll try to work out a few problems in these braking methods soon.